Continuing to look at the climatologies, the next figure is going to show seasonal distribution of zonally averaged meridional section of zonal and meridional winds. Okay, winds have zonal east-west component and a north-south component, and there are specific constraints on how strong they can get as well. As you can imagine, that the Coriolis effect increases rapidly as you go off the equator towards the pole, so moving north-south is going to be more restricted because of Coriolis effect on a rotating planet. Again, we look at seasonal distributions, so JJ, SON, TJF, and MAM. Here, light blue shading in the upper panels denotes zonally average easterly winds. In meteorology, when we say easterly, the winds are coming from the east. When we say westerly, they're coming from the west. Red arrows denote the direction of the meridional wind. Solid red curve shows 500 hectopascal zonally averaged vertical velocity, which tends to be orders of magnitude smaller than horizontal winds. So things move very slowly in the vertical, except in the very strong convective regions and so on. Okay, so hard to include both the figure and the caption, so I'm just going to show captions before or after depending on whatever is convenient. So we are looking at zonal winds, June, July, August, September, October, November, DJF, MAM, just because it's showing both zonal, meridional. So think of it whichever way you want, arranged kind of funny, but nonetheless. Starting with the boreal summer, you will see these shadings are easterly, so there are negative numbers there, even though the contours are solid for both positive and negative. And immediately you see these strong ducts of very high wind speeds in zonal sections in both hemispheres, which move with the season. So you can see that the winter hemisphere in south of the equator in June, July, August has stronger core upper level winds as westerly, so going from west to east, weaker here and stronger here in the summer, and so on. And these are the trade winds near the surface, and as you go into the upper atmosphere also there are easterlies, and you get westerlies once you get off the lower latitudes, especially away from the out of the Hadley cell sinking part. And these of course are the jet streams. There is actually two jet streams, the subtropical and subpolar jet streams, but polar jet streams, subtropical and polar jet streams. There is also stratospheric jet stream, which we will not worry about right now. The polar jet streams are obviously much stronger, even though during an El Nino the confluence of the subtropical and polar jet streams do matter for producing massive amounts of rain over California and so on. What else can I say? You can see the seasonal contrast, as I said, plus notice that these westerlies have a vertical shear, so weaker near the surface, getting stronger in the vertical. And we will relate this to the temperature in a minute, where the we already looked at temperature before. Warmer temperatures here, colder temperatures there. So where the meridional temperature gradient is strong, you get strong vertical shear because of what is called thermal wind. Okay, so horizontal gradients of temperature produce vertical shears in zonal winds because of geostrophy, another term we haven't defined it in case you are new to this. On a rotating planet, if you look at weather charts, for example, you'll find that winds are actually flowing along constant pressure lines. This is very unique. Instead of going down the pressure gradient, because of rotational effects, pressure gradient can be balanced by rotational effect to produce winds along constant pressure lines. That's basically geostrophy. And geostrophy works very well to explain the homogeneous fluid flow, but when you have non-homogeneous fluid with horizontal density gradients, and you still have other conditions like low friction, etc. You can still get geostrophic balance, but then you will get vertical shear to balance the horizontal gradients of temperature. So I'm saying that in words, but we'll come back to that equations and so on in later chapters. So obviously, as the sun moves to the south in December, January, February, you get weaker jet stream here and stronger jet stream there. It also wobbles more in the winter hemisphere. You can think of that as basically a referee between cold polar air masses and warm subtropical air masses, and the wobble, especially now producing lots of wild weather, warm somewhere, cold somewhere, going from western US, eastern US, Europe into Siberia and so on, is created by those wobbles in the jet stream. But you should also be amazed that the westerlies also occur at the surface. Westerlies means what? The Earth itself is going from west to east, and the winds are going faster than the Earth. So despite the friction near the surface, winds are zipping along faster than the Earth because you are putting momentum down from above to below. So we'll see that angular momentum requires that Earth move angular momentum or impart angular momentum to the atmosphere, and atmosphere moves it poleward, and that's why you get these strong westerly winds and so on. Okay, quickly, meridional winds, very different structure, not so well organized at all once you go beyond the low latitudes. So you have strong cross equatorial flow near the surface here, going from the winter hemisphere into the summer hemisphere. So that's the convergence into the intertropical convergence zone, or the rising motion needed for producing rains, we will see in a minute. And at the upper level there is opposite crossing into the winter hemisphere from the summer hemisphere, and it changes direction in the other seasons. So this is the boreal summer season, and this is the boreal winter season. And in the equinoctial seasons you get a more complicated picture of convergence here and divergence there, and not so strong cross-equatorial flow and so on. So there is the equinoctial pictures for the zonal winds. Okay, these are associated with the sea surface temperature distributions, which we saw as a zonal mean meridional section. So in the summer, briefly, Indian Ocean is very warm. West Pacific in maritime continent together form this Indo-Pacific warm pool. This is the intertropical convergence zone that we will come back to, which extends on here as well. And you can see, if you look carefully, that in the boreal summer, when the sun is to the north, there is more warm water to the north, and as sun goes to the south, the entire thing shifts south, but the Indian Ocean remains warm. And you can also see very strong contrasts in temperature over land, summer versus winter. Huge differences in temperature compared to the ocean, because ocean is deep, has very high heat capacity compared to land, so obviously doesn't warm or cool as fast as land. Obviously this makes a difference for land ocean temperature contrasts, which become critical for monsoonal circulations and so on, which we will see in some detail later on. Okay, so I'm just going to do these as little podcasts combining 2 or 3 images together, but you can weave the story together by watching the podcasts as you wish. Okay, but as I said, you need to remember these basic features like the back of your hand for your research, if this is going to be your field, or even if you're doing hydrology or ecology or whatever else. Okay.